Hello, everybody. So today we talk about the system design of Uber. So Uber is the app in which a user can request a ride, and so user would like to go somewhere and inputs the destination, and then user can see the list of fare estimates, and if it looks good to the user requests a ride, and there is a matching process, and if there's a driver who'd like to take him to the destination, so the driver accepts the request, and then there's a match, and after the match the driver goes to the user's current location or maybe meetup location, and then the driver drives him to the destination, and yeah, is that it? Okay, so I will go with the function requirement. So as I said, a user can search fare estimate with input like start location and destination. And also user can, let me change a little bit, user input, so the fare estimate. So I would like to display multiple fare estimates. So for example, according to the car types, maybe large type or small type of cars, or maybe based on the time the user has to wait until the driver's arrival, there's some fare estimate. And if user and now user choose a fare estimate if it looks good to him and requests the ride. So request the ride means that the user agrees to pay if there is a driver, kind of. And now the problem is how the driver can know the user who'd like to, take a ride. So the system should send the notification to the drivers. The driver receives the push notification about the nearby request. Okay, and now driver can accept the request and match with the user. Okay. Now there is a match, and the driver, goes to the user's start location. So definitely the app should navigate the driver to the user's start location, and then when they meet, again the system should navigate the driver to the destination, but I will make them out of scope. And also I will make the payment process out of the scope in this case. Okay, so these are function requirements. Okay, so for non-function requirements, so firstly I'd like to go with the cap theorem. So cap theorem is out of the strong consistency, availability, and partition tolerance, the system can guarantee up to 2 of 3. So because we are developing the distributed system, partition tolerance is the must, and I have to choose out of strong consistency versus availability. So I can rephrase this as, if I take the strong consistency, the kind of process, maybe the request handling process or maybe some process in the server, can read the latest data, including the latest write to the data. But availability is not guaranteed. So if the data, if the latest data cannot be returned, the process cannot get any data. But if I choose the availability, it means that the process can get the data always, but the data may not be updated, which means that the data may not include the latest write result. So that's the kind of comparison between storm consistency versus availability choice. So that being said, in this system, for matching, I will go with the strong consistency. And for others, I will go with the availability. So the reason why I need the strong consistency for matching is, let's say there is a driver there is a user who made the request, and there is one driver whose process, driver's request handling server process, read the data and assumes that the request is not matched by anyone. So that process accepts the driver's request and they match. However, if I don't guarantee the strong consistency, there is another user, even though the match data is created in the database, there may be another driver who reads the matching status of the request, but it cannot read the latest matching status, and outdated match searching status is read. So in that case, what happens is that two drivers match with single request, which means that the first driver the first driver's match is updated, or I should say overwritten by the second driver's match. So this is a problem. So that's why I try to guarantee the strong consistency for matching. But for others, availability, eventual consistency is fine, because for example, let's say, user would like to see the driver's latest location. For that one, it doesn't have to be updated. It totally finds that the driver's location is a bit old, like 5 or 10 seconds ago, even though the user should be able to see the driver's location. So I guarantee the availability here. Okay, so next I will go with the low latency. So for low latency, I think this is kind of tricky, because when I think of the case of the real Uber, fare estimate is not something which is returned within 1 second. Yeah, so I will give a kind of, enough time for fare estimate. So let's say fare estimate should be returned within 5 seconds, and request the ride. Yeah, this matching process, I will give 1 minute of the time. So user has to wait up to 1 minute, and if user cannot, the system cannot find the match in that 1 minute, user now see that in the app which says the driver couldn't be found. And for others are basic API call. So let's say within 500 milliseconds. Okay, so this is a latency requirement I define here. Okay, and finally I will write scalability. So let's say scalable to 100 million data active user and 15 million write per sec. Sorry, 15 million writes per day. And yeah, this is the scalability, but also I have to take care that this Uber system experiences the kind of spike of the requests and matches. So let's say there was a kind of baseball game in the stadium, Dodger Stadium, and there are so many users there, and they want to drink, so they cannot drive home. So they, after the game, they, request a ride in Uber at the same time. Maybe 10,000 million users, maybe 20,000 million users request at the same time. So in that case, I can say this is a spike. So I have to take care how I can handle it. Okay, so these are non-functional requirements. Now I will talk about the core entities. The core entities are database table names, and I will list them so that I can use them in the API designs later. So we need, of course, user and driver. Yeah, of course, there's a discussion that user, for single user ID, it can make a role of user and also driver. But for here, I will separate them as the mother. So, and maybe we need location and fair estimate. And fair estimate and request right, so request. And we can say ride. So ride is the, I will write it down here. This is the matched request. But I would like to create another mother here as the ride, because for ride, there's so much information it has to store. So like matched at, or I should say drivers, evaluation or something like that. So I separate and create the right model. Okay, so these are the kind of entities I have to take care. So maybe one more thing. We have to, persist kind of driver's response about the, request. So I would create another core entity here as driver response. Okay, so I will do the API design. So I will firstly quickly list the name of the APIs. So firstly, user can input start location and destination and see fair estimate. The first function requirement for this, we need the get fair estimate API. And then after user gets the fair estimate, user chooses a fair estimate and requests a ride. So I can say request a ride API. And then in functional requirement number 3, driver receives a push notification about the nearby driver request. So there isn't any API needed here. And for the last one, driver can accept the request and match with the user. So here, this is something like submitting the driver response API. And once this driver response is submitted, the server-side system creates a match and set it. Okay. And one more thing I have to take care is about the location. So I didn't mention that much, but of course, here in function requirement number 3, driver should receive the request about the nearby users. So we need the location of the driver and also the locations of users. So for each, I should say for each of them, I mean for either of them, they should make the update location request, and server side should persist this. Okay. So now I will talk about the detail of the API. So for this one, because he'd like to get the fair estimate, I would say this. But fair estimate is something created by this API. So I use the post API. And of course, we need the authentication. So header should include the session token. With this, our backend can know which user the request was made by. And now for the request body, we need the start location, probably longitude, latitude, yeah, and also end location. Of course, maybe this can be kind of park or maybe station name. But for system, I will go with I will think of the longitude, latitude. Yeah, and now this should return 200 in the happy case. So in the happy scenario, this should return the fair estimate. Okay. So number 2, request ride. So ride is something requested from fair estimate. So I would say this is fair estimate ID and we want to create a ride. So I would go with this. But this ride is something which should be created. Sorry, so I will use a post. Otherwise, what happens is that when user makes the ride request again and again and again, this, ride record is replaced with the request. But of course, but on the second side, this should be post request, because obviously ride is something created, from this fair estimate. So this is not something replaced every time when this request is made. So this request ride should be created only once. So yeah, so I use the post method. And of course we need the header, which includes the session token for authentication. And for this user, what is it? So request ride. So we need the fair estimate ID, but this is already included in the path. Yeah. So maybe only this. Okay. And okay. So yeah. So where I was talking. So request ride. Yeah. Oh, sorry. So this is request ride means that create a request. So I would say create request or maybe make request. So what I would create is actually a request. Ride is because much request. Yeah. So post fair estimate ID request creates the request, single request under specific fair estimate. Yeah. And when the request is created, this should return something. Yeah, maybe just 204 is fine. Oh, no. We need to return request ID. Okay. So now I just noticed that I forgot something, because when after user makes request, he'd like to know what happened on the request. So if the driver has found a node that something the client has to fetch. But the problem here is matching can take up to 1 minute, and it is a bad design that the client is connected to the server with HTTP request. HTTP connection for a minute, because it is quite likely that there is a kind of network disconnection within that 1 minute, and user has to make the request again to, yeah. So instead of that, I'd like to use the short polling here, and I can use the short polling here and not the WebSocket, because this, polling period can be, let's say, 5 seconds or something. So it doesn't have to, it doesn't require the near real time short interval like sub-seconds. So basically, WebSocket is really quick near real time, but the weak point is that the infrastructure setting is so complicated. But for short polling, infrastructure is easy, but the problem is, relatively low, so relatively late update from the, not near real time update. And also another problem is there's so many intensive requests going on, and servers is overloaded with them. But for this, because 5 seconds of polling, short polling overloads the server if the polling period interval is, let's say, 1 second or sub-second. But in this case, the update with 5 seconds of delay is completely acceptable, and it means that the short polling period can be every 5 seconds, and I can say this doesn't overload the server compared with WebSocket. Compared with the case, short polling with very short polling interval. So in this Uber system, I can use the short polling. So fetch request status. So I forgot this. So get. So this, the server side should return status, which is maybe matching or matched, or matching not found, driver not found. Okay, so this is fetch request status API. And for submit driver response API, so this is something which is submitted on the request. So I would go with request and submit driver response. So because driver response is created only one for each request, so I would go with the pod and singular response here. And samely, I need the header, and now this should return 200. Yeah, and of course we need if the driver match or not with result. So matched. Yeah, I would say it's matched Boolean. Okay, so finally we need the update location. So which here I use the put method for location singular, because location is single, only one for each user. And now with this, they should return 200. Yep. Or maybe in the failure case, it should return 500 something, but I will talk about the happy scenario here. Okay, so these are APIs. So from here, I will do the high-level design. The goal of the high-level design is to meet the function requirements. And to meet the function requirement, I will implement these APIs one by one. So firstly, I can say there are two kinds of client. One is user and the other is driver. So I will put them here. And for backend, I will go with the microservice architecture because in the end, this system has to scale and there should be so many features in the end, I assume. So I'll go with the microservice architecture. So with this, the system can be separated into microservices per domain. So the separation of the domain is quite clear. And also, even if there is a kind of issue in specific microservice, let's say there is a problem in the matching service, still the driver's navigation service can keep working. So this kind of for tolerance is quite important. So I'll go with the API gate microservice architecture. And I will implement get fair estimate API. So user makes a request to server side. And this is routed into the, let's say, matching service. So the request is routed into matching service through API gateway. So API gateway does the routing and also authentication and also rate limiting. Okay. So now matching service has to know, creates the fair estimate, and I will make it a kind of black box here. Of course, we need the kind of machine learning algorithm to decide the price. Yeah. For example, at night, it should be more expensive. If there are many riders who are looking for the driver, it should be more expensive or something like that. So I will create fair estimate service and I will make it a kind of black box. So this matching service fetches the fair estimate and return it to the user. Yeah. But for here, I will persist fair estimate in the matching service. I will talk about this later, but in a system, we kind of need the, we have to create the right request object from the fair estimate. So, and it's quite convenient if fair estimate recorded here in a database rather than the database in the fair estimate service. So I put it here. And of course, the most important thing is fair estimate is not updated later. So I don't have a concern for the data inconsistency between this service and this database. So I, save it. So create fair estimate. So for I will use PostgreSQL. So, but this is kind of, the reason why I use PostgreSQL here is because it's this industry standard. But if there is a kind of requirement, specific requirement for this database, I will replace this with maybe DynamoDB or maybe Cassandra or maybe some other yeah, database, maybe Redis. But here we, of course, we have to persist the data in the disk, and so we don't use Redis at least. So first may need ID and request user ID. Request is kind of confusing, so I just say user ID, and where just the price, and start location and end location. And created a timestamp. Okay, so these are the first made table attributes. And now first made record is created. So the first API is implemented. The second one, make request. So user would like to make the request. And yeah, so based on the fair estimate rendered in the front end, user chooses one of them, or maybe user don't choose any of them. But after user chooses one of them, it should be submitted to the matching service. And now this matching service should create the right record in the database. Sorry, request record in the database. So we need I can say this user ID is kind of redundant because from this foreign key, fair estimate ID, I can see which user triggered this. But for the performance optimization purpose, I put user ID here. And of course, user ID never changes for these two tables. So user ID requested add timestamp. What else? Request made user ID. Yeah, and of course we need kind of status. So this should be matching, or I should say searching, matched, and not found. Okay, so now I've implemented make request, and I will talk about fetch. Oh no, so based on this request, I have to notify driver about the request. So here I use the change data capture of request table, and there should be the service which searches for the driver. So I'd say request service, maybe driver search service. Yeah. So now this driver search service finds the driver who are close to the request user. So we need the location. So I will talk about that next, but based on the location, this driver search service filters the drivers who are currently close to the user and looking for the ride. Am I correct? Looking for the ride. Looking for the, yeah, ride. So, and after that, this would like to send the notification to the each, drivers. So I would put notification service here, and this driver search service makes a request to notification service, and this will make an API call to, let's say, third-party Google Firebase message API, or for the iPhone users, it sends Apple notification service. So yeah. So now notification service makes a request to the third-party API. And this third-party API now pushes notification to the driver. Okay, and now driver submits the driver response. So this sends a request here, and the request is routed into the matching service, and now this creates the driver response record. And also, not only that, if there is a match, it should update request.status. And also, it has to create the right record if there is a match. Okay. So these things should be done from the matching service. And for the date consistency purpose, I make these changes in the single database transaction. Yeah, because I chose PostgreSQL for now, this PostgreSQL, I can use the transaction of the database. So here I create driver, response table, and this should have the request ID and the timestamp, and the most important thing is if he accepted the request or not, Boolean. And of course, driver user ID. Okay. And for the ride table, we need the request ID and driver ID. Matched at. And of course, status, like so, like picking up, or maybe driving, or finished, completed, or something. Yeah. Okay, so these are the ride table attributes. Okay, good. And one more thing I was missing is update location API. So this is used by both user and driver. So they make the request to update location API, and the request is routed into the location server. I create another microservice here from matching service because the request pattern is different. So this is quite intensive API because in case of Uber, the driver's accuracy is so important. So the driver and also user client has to update their location every 2 seconds, 3 seconds. So this is completely different from matching service, yeah, whose request load is relatively light. So I use location service. So this location service should persist the location data into the database. And here I separate the database. The reason is because this location update query is quite intensive. So I will talk about scalability later, but at least I'd like to separate database so that this doesn't affect the RightDB performance. And also, I can imagine that we need the, kind of location and geolocational query. So maybe we have to use the kind of specialized database like Redis geohash or maybe Elasticsearch or something like that. So I separate it from PostgreSQL. So this update location is done here. Okay, good. And I forgot to say, but of course, this driver search service has to make the query to filter the users who are close to the rider user. So there is an arrow here. Okay, so this is the this system design meets the function requirement. So yeah, this is it. I will talk about the non-function requirement in tomorrow's video. Yeah, especially for strong consistency on the matching and scalability. But this is it. Okay, so that being said, I finished my today's system design practice. Thank you so much. Bye.